electrical engineering from the University of Engineering and Technology, Peshawar, Pakistan in 2007, and a double PhD degree in electrical and computer engineering from the Hong Kong University of Science and Technology, Hong Kong, and University of Western Australia, Perth in 2017. From 2008 to 2012, he worked as assistant manager in NESCOM, Islamabad, and currently he is a postdoctoral fellow with the College of Science and Engineering, Hamad bin Khalifa University, Education City, Qatar. And his research interest mostly tilted towards the mixed signal IC design and CMOS readout interface for MEMS devices, image sensors, analog digital converter, and mainly we can see that all of that is majorly focused towards the mixed signal design. And he successfully taped out multiple mixed signal modules, including some sensor nodes and the image sensors. And I would like Dr. Moaz Ahmed to take on from here. So thank you very much for your time. You can take on from here.
Yeah, thank you very much, Dr. Hassan. Am I audible to everyone?
Yes, you are clearly audible.
Okay, thank you. Yeah, so today I'm presenting design techniques for precision amplifiers. We also call them instrumentation amplifiers. So we'll go through this agenda from introduction of the instrumentation amplifiers or precision amplifiers. Go through discrete components based instrumentation amplifiers. Then we will study the origin of low frequency errors that are inevitable in all kinds of amplifiers. And then cancellation techniques that could be followed to get rid of these errors. Then we go through some instrumentation amplifiers topologies, popular topologies, then recent examples from the literature, then conclude and recommendations. So starting with the introduction, as you can see, we can have any kind of sensor, and the sensor, like the word is analog, so it senses analog quantity, could be voltage, could be current, temperature, fluctuations in stress, strain, all these kind of physical parameters. So these are then, these needs to be amplified, signal conditioned. By signal conditioning means, of course, with the output of these sensors are usually, very weak signals. Could be in the form of current or a voltage or a change in capacitance or a change in temperature or a change in voltage or combination of all these quantities. So we need to amplify this very small change, typically in microvolts or nanovolts or microamperes or nanoamperes, or even the change in capacitance could be in femtofarad capacitances changes. So we need to amplify this so as to digitize it through ADC. And as we all know that the output of ADC is usually in the form of 1, 0, 1, binary output, which could be processed later on in computers, which could be used to, feedback a loop to make an action on this transducer or a sensor. So the typical features of a precision amplifiers are they need to amplify the sensor weak signal, which, as I've already explained, could be in a microvolt range. And then while doing so, they need to, as you can see, the output of the sensor has a DC element as well. So this DC element could be typically, it could be 1 volt. So, and the weak signal is in a millivolt or microvolt range. So we need to amplify only the differential signal while ignoring the common mode signal. So that's called common mode rejection ratio. It usually for modern applications should be higher than 100 dB. So while rejecting the DC bias and the other common mode signals, the interfacing amplifiers only needs to amplify the differential signal. Also, these bias, common mode biases could be near the supply rails. It could be near 1 volt or 1.8 volt if this technology is 1.8, or it could be near ground. We call it ground sensing, like 0 volt. So the input pair of this amplifier has to be biased, should work at all these kind of input ranges. So we also need to provide a very high input impedance for the sensor readout signal, since usually the sensor signal is very weak. So we cannot, if we have a finite impedance of the amplifier, it can easily load the preceding sensor. So this is another important feature of instrumentation amplifier. Also, the non-idealities, we will study it more in detail. The input offset and the noise, they must remain below a minimum detectable signal level. And the and we have to achieve all these characteristics while minimizing the power consumption, because most often these precision amplifiers are deployed in portable applications where we have only limited battery supplies. What are the challenges? Since like traditionally, the instrumentation amplifiers were implemented in BJT technology, which has inherently lower offset and flicker noise. But with time, we see that CMOS became more and more widely used. So it's and also because of the very low cost and integration friendly, like CMOS technologies could be integrated with all other kind of emerging technologies. So, but the problem is that they exhibit higher offset. A typical amplifier or a transistor in CMOS compared to a BJT counterpart, it has higher offset and it has higher flicker noise corner. And for most sensor applications, the noise band that has to be designed white. Like we will see, we have a flicker corner, and then we have a white thermal noise floor. So this this thermal noise floor actually usually starts after tens of kilohertz of after the flicker corner. But the problem is that the sensor signals are usually in less than a kilohertz. Our biomedical signals are usually 10, 20, 30 hertz or 100 hertz or 200 hertz. So they are fully submerged under flicker noise. We have to remove this flicker noise to somehow higher frequencies, and we'll see how we do that. Again, then gain error also of typical +1 -1%, because we implement these gains with the passive components like capacitors or resistors, and with these elements comes the gain drift with temperature, so or with aging. So we also need to somehow compensate these drifts. So let's start with the discrete components-based instrumentation amplifiers. So starting with the if you are implementing the instrumentation amplifier on a PCB or on a breadboard in your lab, maybe as you'll see one of the next designs, some of you would have certainly implemented, because I did that in my undergrad project, ECG, detection circuits. So with the combination of resistors, we can implement a single op-amp based instrumentation amplifiers like this. It's very popular, and it's a simple differential to single-ended converter also. So the input impedance seen by this input V in P and V in N, we can see clearly is not balanced. V in P sees R1, while V in N sees R1 in parallel with R2. So they are not balanced. The common mode ratio of this amplifier is also determined by the matching of resistors, which, of course, this is a discrete type design. So at most we can have 5%, or it's very expensive, 1% matched resistors. So there will always we will have a gain error. And also the maximum achievable common mode rejection ratio of this circuit at maximum could be 66 dB. This comes with the matching of resistor limitation. And the loading of the sensor also is a problem, because these R1, because the sensor sees input impedance, this R1 and R2. This could not be very high, because if you have large resistors, you will have a very large thermal noise, 4kTr thermal noise. So there is a trade-off with noise and loading of and the input impedance of the amplifier. So this is another topology, 2 op-amp based instrumentation amplifier. So here the input impedance of the circuit is now determined by A1 and A2, so which are clearly the input pair transistors. So if they are BJT, they are mega ohm impedances. If they are CMOS, we know that the gate is insulator, so it's technically like infinite impedance. So the input impedance is solved, and also but still the problem with this circuit is the gain dependence of common mode
Mas,
rejection. Yeah,
sorry to interrupt. I think your slides are stuck.
you cannot see slide number 2.
No, now this 2 op-amp slide is visible now.
Or can you see the 2 op-amp based IA now?
Yes, now it's visible.
Okay. So I was talking about this topology. So we have 2 amplifiers. The input impedance of the signals, you can clearly see these. The sensor sees the input pair within these op-amps A1, A2, and if they are implemented with BJT, the gate, the base collector junction, I mean, the input impedance would be in mega ohms. If they are implemented with CMOS, these op-amps are CMOS based, then the input impedance is infinite. So that problem is solved. So the sensor is not loaded, very good. But the problem with this is still A1, if you see the op-amp A1, amplify the common mode signal by a ratio of these R3, R4 resistors. So it's a resistor divider here. So the common mode of A1 sees this gain R3 plus R4 by R4. And it can easily load the, it can easily saturate the amplifier. So we have no amplification room. The gain of this topology is expressed here. It's 1 plus R2 by R1 plus R2 by RG. Now, this is the topology that I was talking about. Like, this is the topology that we have seen while doing lab projects. Can you see the slide now? 3 op-amp IA.
No, still we're still at 2 slide version.
Why is it not?
Mr.
Now?
Hamza, can you confirm that, Mr. Hamza?
Sir, we are seeing the 2 op-amp.
Yes, we are still at the 2 op-amp version.
Dr. Moss, can you again share the screen and then try?
Again, share the screen. Now, can you see the 3 op-amp based IA?
Yes.
Yes, no.
Okay. So here we have a kind of 2-stage amplifier scheme. So we using 3 discrete type amps. Amplifier A1, A2, they form a balanced input stage, followed by amplifier A3, which is the output stage. Okay, so again, the inputs V in P, V in N, they are seeing the differential pair of these amplifiers A1 and A2. So which in CMOS would have infinite input impedance. So again, the sensor loading is avoided. Now, the common mode rejection ratio of this topology is the product of first stage gain and the CMRR of the second stage. So the CMRR of second stage typically is 60 dB and followed by the gain of the first 2. So we can have easily 80 dB CMRR by using, if we use thin film matched resistors, 0.1% precision resistors. And also the large power consumption, and because we are using 3 op-amps, so power consumption is large. So this is its drawback. Now we'll study the low frequency errors that we find in amplifiers, and then the cancellation techniques. Can you see the slide? Typical low frequency errors in amplifiers.
Yes, sir.
Okay, good. Okay, so this is the typical characteristic whenever we bias a transistor. So we will have a certain large power spectral density of noise at lower frequencies, and these and followed by then we have a thermal noise floor. The thermal noise floor is like flat. It's called white noise over frequency ranges. On x-axis is the frequency. So the thing is, where the flicker noise corner meets the thermal noise PSD level, that's called flicker noise corner. And that corner frequency usually is in tens of kilohertz in CMOS amplifiers. The problem is that, as we talked about it earlier, the signal that we usually amplify using these kind of precision amplifiers has input frequency content of usually less than a kilohertz. So this signal is fully submerged under noise. So in order to amplify this signal, we have to get rid of this flicker noise, large flicker noise. Then there is also this red vertical pointer. You can see it's a DC offset. This offset is typically like tens of millivolt, 30, 40 millivolt. And the signal, as I talked, could have amplitude like tens of microvolt. So again, the error has much, like many times more amplitude than the signal to be amplified. The origin of these are discussed. The offset comes from the threshold voltage mismatch, which comes from the doping level where fluctuations when during the fabrication of these transistors. The VTH mismatch offset can also comes from W and L, the drawn. There's a difference between drawn and the actual fabricated width and length ratios. Then the flicker noise corner, this noise is given by this expression where K is a process parameter by WLC. So clearly the frequency is in the denominator. So higher the frequency, lower the flicker noise, and vice versa. Then there is also a drift, which is basically a cross sensitivity of error sources with temperature or time. So if you employ an amplifier in your design, so over time, or as you carry your amplifier to outside or to different temperature zones, so this the gain errors and the offset and other errors, they actually change with all these variations in time and temperature. So that's called drift. So then there is also a gain error and offset error drift. Yeah, we already talked about it. So how do we cancel all these errors? Is this slide visible? Trimming, auto-zeroing, chopping?
Yes, this slide is visible. Dynamic offset cancellation technique.
Good. So there are usually three methods. One is trimming. So trimming is actually done after fabrication. It's employed at the fabrication or the processing facility. So you measure your noise or you measure your offset and you cancel it somehow using some switches or some the gain elements like resistors or capacitors. So it couldn't be done by like in the field. So it cannot cancel the dynamic errors like drift. वगैरह ये cancel नहीं कर सकता trimming because it's only done once. So the better options are auto zeroing and chopping. So auto zeroing is a discrete type approach which is used to reduce offset and noise. We'll study it, followed by chopping, which is a continue time approach to reduce flicker noise and offset. So by employing these two techniques, we can reduce the offset from tens of millivolt to few microvolts, or we can also bring down the flicker noise corner frequency from, without any offset cancellation. It's usually in tens of kilohertz or even hundreds of kilohertz to sub-hertz. Like, when flicker corner is drawn to such a low frequency, then your signal ideally see only the flat noise, like the thermal noise only. So which can be easily designed. I mean, you burn more power, you reduce thermal noise. And then drift can be reduced to tens of nanovolt per degree Celsius by using either of these two dynamic techniques. So can you see the next slide? I have to make sure that we are together.
Yes, we are at the dynamic offset cancellation technique slide. Now that's changed, auto zeroing slide.
Okay, so auto zeroing is sample and cancel offset. So here you can see a typical amplifier. Yeah, can you see my mouse? I think I should.
Mouse is not visible. You can turn on the pointer.
Let me see. I think power pointer is needed because it's sometimes this is. How do I turn on the pointer?
Just go into slide mode and then right click and check if the pointer option is there. Just open the slides.
In the PowerPoint, sir.
In the PowerPoint. Go to the presentation mode.
Okay.
Right click of the mouse. Right click of the mouse.
Yeah.
Maybe that's different for the MacBook. Might be the setting is different.
Yeah, it's actually a laptop.
Because for the Windows, if we go in the PowerPoint and in the presentation mode by the right click.
Can you see the arrow now?
This arrow is now visible.
Okay, I think it should be fine.
Okay.
So see, so we have an amplifier here. Its offset is clearly in tens of millivolt. We need to reduce it. How do we do that? So we employ a two-phase clock, phi 1, phi 2. During phi 1, the switches are open. So we don't have continuity with the signal. Sensor output, sensor is not connected. So phi 1, the OTA is in unity gain configuration. So what it does is actually it samples its offset over these unit capacitors, CS1, CS2. Okay. And these capacitors have the other sides connected to VREF, like phi 1, their switches are closed. So during phi 1, the offset at the output gets sampled at the capacitors connected at the input. Okay. So during the second phase, the unity gain configuration is stopped, like phi 1, these S1, S2 switches are open, and then these switches are closed. So the input, the amplifier sees the input, and it sees its offset again, and then basically the at the end of phase phi 2, we have sampled the offset twice, so we basically cancel the offset. So this topology is basically input offset storage topology. So we can also store offset at the output. So when we store the offset at the output, I mean, both topologies have their own drawbacks, pros and cons. Recently, I just implemented another topology I just wanted to show you here. So this is basically we use two preamplifiers. This is preamp 1, preamp 2, and then followed by a latch. This is our, we call comparator. And then SR latch to, do the non-return zero output of the comparator. So basically what we do is actually we sample the offset of this second amplifier, this second preamp, this offset. Can you see the pointer?
Pointer is not visible.
The arrow of the mouse.
Might be when you are directing at the simulation due to the black background, that might be not visible.
Is that visible now?
I cannot see it, sorry.
Oh, it's a bit. Let me see. Because it's important, I should have this. Just leave it because getting short of time.
You should take your time to set up properly. No issue.
Just 1 second, please. Maxine, can you tell me how to turn on the pointer here? Because I'm presenting. I need to turn because they cannot see my arrow. In the sense, we can use that. On the MacBook, I've not done that before. I thought
If you put it maybe on a non-view, if you save it somewhere, because it's on view only. But you can put on diaporama, presentation mode.
Okay.
Yeah, presentation. That's it.
No, they cannot see my pointer actually.
Go there. Yeah, on the three dots. Use presenter view. What is that? Try it. Yeah.
Now, can you see the pointer?
Just pointer is visible now.
Yeah.
And can you see the, like, is the whole slide visible to you?
Actually, now there are this slide and the next slide that is also visible.
Okay. All right. Yeah. No, it's not. Like, is it, if I keep like this, is it okay? Because now the pointer is at least visible.
Because you're sharing your screen.
Yeah, I'm sharing screen.
Yes, it's
So
fine.
why don't they see the pointer if you're sharing the screen?
Yeah, they should be able to see because it's the ditto copy of the screen, right?
Yeah.
But anyway.
You're using Zoom or
Is it Zoom?
what is it?
It's Google Meet.
Oh, Google Meet. Yeah. Yeah, thank you.
Okay.
Yeah, because pointer is very important because circuits, we have to go through different phases of the circuits. Now, that's why I just wanted to show you whether the screen is, although the screen is smaller now, but still the students, can you understand the circuit now? Like, can you see this is preamp 2, this is preamp 1, this is latch, like the, together they are the comparator. So what we do is actually we sample the offset of the preamplifier at the input over these capacitors, very small t, these capacitors. And we also sample the output of this preamp. The first preamp's output is directly sampled over the capacitors. So basically the capacitors are sampling the output offset of preamp 1 and at the input offset of preamp 2. So we have an input-output offset cancellation scheme here. And they also works the same, like we have a set of switches at the input. These switches are closed when they are sampling the signal. They are open when we are sampling the offset. So at one phase, we only sample the offset and store it over these capacitors. During the next phase, we sample the signals and the offset is cancelled. Now we go to the other method, which is chopping. This is a modulation technique to reduce the offset. Can you see the slide?
Yes,
I
still
hope-
on the auto sequence slide. I think there is some lag in the connection, so it might take a few seconds to change the slide.
Oh, it might be. Yeah, it might be. Although it's very fast internet. Let me do nothing. Just wait to see if it's okay. Please tell me when it's visible.
Now it's visible.
Okay, yeah, it was lag. I didn't do anything. Okay. So chopping. So chopping is basically, it's very simple. Let's see, we have a DC signal, V in. We have a set of switches. So we have basically polarity reversal switches. So during, let me tell you here. So during this phase, the input is just passed through the chopper, like these polarity reversal switches, unchanged. So at the output, you observe the DC same as it is. During the next phase, we reverse the polarity of these switches. And also, Hassan, can you see my pointer?
I cannot see your pointer. From student, can you see the pointer? At previous slide, it was visible, but again, it's not visible.
No, it's not visible, sir.
Yeah, sorry for that, man. I should have. Yeah. Anyways, so so the thing is, we pass the signal through one set of switches, followed by the other set of switches. So this is since the polarity is reversed, so we see the same signal for the next half period with opposite polarity. So together, what we have seen is we have converted a DC in a square wave signal. So, and the frequency of that square wave is directly proportional to the frequency, of course, is the frequency of the chopper. Like how often we change the polarity of the switches determine the frequency of this output wave. So this is basically the conversion of DC into a, so in another term, like how we multiply the amplitude modulation or frequency modulation is what we basically multiply input signal, a DC signal with a high frequency AC signal. And we modulate that DC to the multiplied signal frequency. And then we have to bring it down also. So here we see the time domain operation in another view. So we have this polarity reversal switch, chopper switch. So this is basically a set of 4 switches opened at, 2 phases of chop frequency, FCH and FCH bar. Can you see the slide now? I think it will take some time. Does it happen with other presenters as well? Like it takes time? There is a lag?
Actually, we are observing this for the first time.
What could be the reason? Google Meet. So now chopping time domain operation is visible, right?
Yes, now it's visible.
Okay. So the first figure is the polarity reversal or swapping switches, followed by a typical, how do we use these or deploy these chopping switches in actual amplifiers. So we have an amplifier OTA1, an amplifier OTA2. So we deploy the chopper switches at the input and the output of OTA1. So basically the input signal is basically multiplied with this chopping frequency. And together with the offset, of course, offset is a DC signal, and the input, the low frequency input. So they are basically modulated to the higher frequency. Below this BE, you will see the time domain operation of how is it happening. So the input signal V in is shown DC here, and the offset, this is of course overlapped with some offset. Offset is another DC signal. So the output, at the output of this chopper, you see the input has been converted into this square wave signal. And the output of the second chopper, you will see this third expression. Can you, I think if you cannot see my arrow, actually, this is very important to see the where I'm talking about. So the third, from the bottom third figure is basically it represents the output of the chopper. So the square wave has been demodulated back to the lower frequency, and by applying a low pass filter, we get rid of the chopper non-idealities. We'll discuss it. Like there is a chopping ripple, and so all these non-idealities can be get rid of by using a low pass filter, because our original signal, amplified signal frequency is low. It's like it's typically tens of hertz or hundreds of hertz. So this is the next slide. Discuss chopping non-idealities, like the chopping ripple or the residue offset that occur whenever we have this chopping operation, because this chopping is done through a set of switches, and the switches are implemented by CMOS transistors. And the CMOS transistors, when they open or when they close, so they have injection of charges in the channel, as expressed here. So these charges, they actually, when you turn on the switch, I'm sure you guys would have studied, charge injection or clock feed through. So these are due to these non-idealities of the switches that we can have input current, which is represented by this offset current at the input, R1, R2 resistors there. And we can have a chopping ripple. And the expression of these ripple and the offset voltages clearly sees there is a trade-off between the chopping frequency. So if we have high chopping frequency, the ripple is small. The problem is that the higher the chopping frequency, the residue offset is also large. So you have to actually, based on your specification, choose the chopping frequency, which must be larger than the, of course, flicker noise corner. For example, if your flicker corner is 10 kilohertz, your chopping frequency should be 10 kilohertz at minimum. So typically we have like 12, 15 kilohertz. But it shouldn't be large enough to cause a significant residue offset. So this slide just illustrates the trade-off between ripple and residue offset. The next slide is based on the comparison of offset and noise cancellation schemes. So here we compare the two techniques, the auto zeroing with the chopping. Can you see the slide?
No, it's not visible yet. It's visible now.
Okay. So comparison of the two schemes. For instance, this red dotted red line. So this is your signal bandwidth. Like this is your input signal. So if you don't do anything, you have this dotted line like flicker noise. Your input signal is fully suppressed by the large flicker noise. So to get rid of this, if you imply auto zeroing, so you have this dark continue line, which is a little above the dotted red line. See? So this indicates that because of auto zeroing, since that is a discrete time operation, so there is a noise folding. So the input amplitude is a bit higher than the thermal noise floor. Like if your thermal noise is 10 nanovolt per square root hertz, your this raised input could be like 15 or 20 nanovolt per square root hertz. So you get rid of flicker noise, you get rid of offset. But the problem is that net achieved noise floor is a bit higher because of noise folding. That comes inevitably because of the operation of auto zeroing, the discrete time operation. In contrast to this, by employing chopping, you will see this red dotted line. So the chopping, you have lower noise floor. So if you have ultra low noise instrumentation amplifier requirement, you should use chopping operation. But the problem of the chopping is that, again, near the chopping frequency FCH, you have a ripple. You will see in frequency domain, this comes as a it started to increase to large value. So you basically here you see that why we need a low pass filter. You need to get rid of this ripple or this high frequency content, unwanted content after chopping. The good thing is that your achieved noise floor is lower, is almost as what we have the thermal noise floor, equal to the thermal noise floor. So this is so if you need ultra low noise instrumentation amplifiers, usually it's a better option to employ chopping. But if getting rid of the chopping ripple is a problem, if you need simplified precision instrumentation amplifier, it's better you stick with the auto zeroing. Next, we go through the popular topologies of precision amplifiers. Starting with the switched capacitor instrumentation amplifiers. I hope you see the slide 22 now.
It's still not visible. Dr. Moss, I think
Yep.
can you rejoin the session? Maybe might that help to remove this issue, because we have conducted all of the sessions on the Google Meet and never faced this issue. There might be some issues during connectivity. If you can rejoin the session, then that might help.
Okay, like I rejoin using the Google Meet.
Just
Huh?
leave the session. Just leave the session and rejoin. That might help.
Okay, all right. Let me do that.
Sorry for the inconvenience.
Hello.
Yes, you're audible.
Yeah, let me present the slides now. Send my screen. Hello. Yeah. Can you see the slide?
Yes, I can see the slides.
Next slide. Can you see that? Capacitive coupled instrumentation amplifier.
Yes, that is IIT topologies. Can you go to the next slide? Let's see if they are changing.
Next one.
Yes, that's visible.
Current,
That's
current
changed.
feedback.
Yes, that's changed.
Good, good. I think now it's better.
Yes.
Yeah. So yeah, this is the important stuff. Maybe student Hassan, how many students, in your opinion, are following this? Like, I mean, they know about amplifiers. Anyone doing something on instrumentation amplifiers? Like some of this work, like chopping. Anyone has done chopping before or auto zeroing before?
Actually, I think this kind of work, we have just covered the mixing license course, how to do all of this offset cancellation, this kind of stuff. The theoretical part is, and some lab stuff is already done. But for the perspective of project, none of students have done this kind of work. But still they have some rough idea, and they have done this in the lab work. This kind of basic stuff.
Okay, okay. So yeah, because I would like to take question if I mean I don't want to just go through it for the sake of it. If they want me to stop somewhere or if they want me to explain something else, like something better, these are the previous slides. They are easily changing now, right?
Yes, they are easily changing now.
Yeah. So we just so there are two. So dynamic offset cancellation, we have like auto zeroing and chopping. So both of their own pros and cons. And this slide explains like typically by using chopping, we can have a lower noise floor. The problem is the chopping ripple. For that, we need a low pass filter or a ripple reduction loop. We'll discuss some of the ripple reduction loops later on. If you employ auto zeroing, we don't have to do low pass filtering later because there is no ripple thing. The problem is that because auto zeroing is a discrete time operation, whenever you have a sampling, it comes with a some of the out of band noise gets in band. There is always noise holding. So in the end, you have a raised noise floor. So this is the problem with the auto zeroing. So that's why you see there is a difference like this black. Can you see the arrow now, Hassan?
Arrow, actually, I cannot see. Can I
Pointer, yeah, pointer. I have to get rid of this. Maybe some later time. Yeah, I'll do some mock-up with the friend and learn how to do that. It's very important actually because in the circuit I have to explain what is happening. Like this is switch opening, that switch closing, and all that.
Actually, it's not visible to me. Can anyone other from the students confirm that the pointer is not clearly visible?
Pointer is visible, but it's not moving. I mean the arrow.
Arrow is not what?
Arrow is visible, but it's not moving. You can maneuver on the screen. So
I'm hovering. I'm hovering it. I'm moving it now.
No, it's not moving.
Can you?
Yes,
Yeah,
the arrow is not showing moved. It's still
the arrow is
the
not
outside.
moving. Yeah, although I'm moving it. Anyways, yeah. So you'll have these PPTs. Please get back to me if you need any discussion or anything. So we'll discuss more. But the idea is actually to go through, because this is one of the most used work in analog circuits. Like whenever you have sensors, you need to amplify the signal out of the sensors. So whenever you do amplification, you come up with all these challenges. Like the amplifiers have their own inherent offset, noise, and all that. How to get rid of that? We have two of these dominant methods like CDS or auto zeroing, correlated double sampling the CDS, and or chopping. And both of them have their own core. And once you have these operations, then there are the precision amplifier topology itself, which we are talking about now. Like this is switched capacitor one. So here we have a set of switched capacitors that determine the gain. See? So the gain of this amplifier is simply the ratio of input capacitor with the feedback capacitor, right? And typically in IC designs, integrated circuits is usually easier and better to have capacitor matching. Like the capacitors can match 0.01%, while with resistors you can have at most 0.1% matching. So with the help of capacitors, if you are using capacitors as again defining element, you can have more precise gain definition. So this is the point. Since this is again a discrete time operation, because you are sampling, you have opening and closing of the switches, so the continuity of the signal is not available. So again, noise folding and KT by C noise will occur because this is a sampling operation. So either you use two of these amplifiers in a ping pong fashion, like in parallel operation, like in during one phase when the upper amplifier is conducting signal, the lower one is sampling the offset. The next phase, the lower one will be sampling the offset, and the upper amplifier will be doing the signal amplification. So by using the two of these in parallel, we can get rid of this non-continuity problem. We can have a amplification of the sensor signal. Another thing is the input impedance degradation. See, looking from the input side, the input impedance is defined by this expression, 1 divided by F C in. So the problem is, if you have higher frequency, if your F sampling frequency is large, your impedance drops. If you have large sampling capacitor, your input impedance drops. And we all know that lower input impedance is not a good thing, because it loads your preceding sensor. The sensor signal is usually a weak signal. You don't want to load it. Okay, next.
Dr. Moss, can you come back to the previous slide?
All right. Yes.
And as you were discussed that we should involve our students also in this kind of discussion. Sir, can you go back to the previous slide? And I would like to discuss with some of the fellows. They like these kind of structures. The previous one? Yes, this one. Okay, Mr. Zuhair, can you recall this kind of structure we have studied already? There are some kind of integrator that is implemented by this kind of manner. Mr. Zuhair, are you there?
Yes, sir.
So can you see in the class we studied some kind of integrator, the circuit was very similar to this kind of implementation. But this is now the gain element. Why it is not integrated?
What, sir?
It is integrator or gain element?
Just gain element.
Why it is not integrator? So if, as we saw in the class, integrator is also the same during the 5-1. The capacitor C is charged, 5-2, capacitor is discharged.
Yeah, that's a good question.
Delayed.
Anyone else from the class? Anyone else? I think I have to point Mr. Zair. Can you turn on your mic?
Yes, sir.
So the circuit shown here, is that the gain element or the integrator?
Sir, that is the integrator. We have switch capacitor as a resistor, and we have capacitor there.
But here we can see that during clock phase 5-1, if you see that the 5-1, that is input and output are shorted. So that is the resetting phase. So that's why the indicator changed to a gain element.
Okay, okay.
So kindly go through into this kind of nitty-gritty of the circuit, because just by a simple small change in the connection or polarity, the whole operation of the circuit can be changed. And during this kind of discussion, you have to pay attention to these kind of technicalities. Dr. Mas, I think you can continue now.
Yeah, thank you. Yeah, so I wanted to include the students in discussion, but somehow, you know, the arrow problem. And anyways, this is the next topology. Here again, looks like similar. Like we have capacitors, we have op-amps. No, here we have choppers. Like previously, we do auto-zeroing, like we are sampling the offset along with the sampling of signals, and we are cancelling that. So here we have a chopper. So chopper is what? Is the swapping of switches, actually. Set of switches which are swapped. So the clearly with the symbol itself, you can see. So this is a capacitor-based, we call it capacitive coupled instrumentation amplifier. So this ensures a common continue time operation. The gain of this is again, the gain is determined by the ratio of capacitors. So it's very easy, C in divided by CF. So how does it work? So the input signal is clearly is chopped first. So it's converted into, the DC signal will be converted into a high frequency signal. That's why the signal is not blocked by the capacitors. See, if the DC sees the capacitor right away blocked, nothing could be done. But because of the chopper, so the signals have been modulated to high frequencies. And that modulated signal is then integrated over here, over the feedback capacitor CF. And then there is a demodulator, another chopper, we call it demodulator. So this kind of circuit is very popular in biomedical circuits. The input impedance again is directly traded off with the chopping frequency and the sampler switch capacitor C in. Then there is the third topology. We call it current feedback instrumentation amplifier. So this has become quite popular as a general purpose instrumentation amplifier because it ensures the common mode, the continue time operation, and it also doesn't have any noise folding. So here we have two set of transconductors, GM in and GM FB feedback. So both of these transconductors convert the input and the feedback voltages into corresponding currents. So this GM feedback, you will see if you pay attention. This is basically connected to the middle of the resistors RA, RB. And this RA, RB, this is a resistor divider with the voltage, output voltage, V out. And the gain of this precision amplifier is determined by this expression, is basically the ratio of the two transconductors and the resistor divider, RA plus RA, RB divided by RB. So basically, for to simplify the stuff, these two transconductors have usually are identically designed because there is also always a transconductor mismatch also because these are implemented with the input pair transistors. So they are well matched. For that, they are usually like equally sized. So if GM in and GM feedback are same, so the gain is essentially determined by the ratio of these resistors, RA and RB. So these resistors are, they could be implemented off chip, and we can have a very good laser trimmed, good matched resistors to have a very excellent gain definition, or they can be implemented on chip. But again, the gain accuracy of this will be lower than the previous two cases where the gain is determined by the ratio of capacitors. Capacitors are well matched compared to resistors. So this is the problem with this topology. The good thing about this is that it has an excellent common mode rejection ratio and very high input impedance, again because of the transconductors that we see, the input signals see. So in CMOS, it's infinite input impedance. So now I will discuss some topologies, popular topologies. This is implemented by, can you see the chopper and auto zero offset stabilized CMOS IA?
No, we are still at the previous slide.
Now we are covering some examples here.
Yeah, we are still stuck at the previous slide. I'll take some time for the change. Now, yes, now it's visible.
I don't know why this lag start happening. My internet is very fast. In Qatar we have like hundreds megas. No problem.
It's a case change for us as well, because that's first time we are facing this much lag.
And is there a lag in my voice? Like, can they hear me?
Voice is crystal clear. There is no lag in the voice. Only slight change has some
I
lag.
wish I can have the mouse arrow, because I know this is a bit complicated circuit. The mouse is very much important. I miss that. Maybe Hassan, some other day, if someone is interested, I can conduct this again. I mean, no problem for me, because I know I've been a student. I know without a mouse or without a pointer, it's very hard to understand this.
Yes. Inshallah, we will try to reschedule that again. But I think
We will reschedule. Yeah, and for that, I'll try to solve it. Otherwise, I'll be presenting on my computer, like desktop. This is on laptop actually. I didn't have a microphone, so that's why I'm using laptop from someone. Yeah. So it's usually uncomfortable feeling when you are with someone's laptop.
Yes.
Anyways, yeah. So this is can you guys see? It looks very daunting, very complex, but it is not. It's very simple. Like it's set of transconductors only. Like there are two paths. One at the top. You see G21 and G22, followed by an output stage G1. See, so these G1, G2, G21. These are all actually transconductors. Very simple. You would have done that telescopic stages or folded cascode stages, and I'll show you transistor level implementation also in the end. One of my design. So basically, it consists of a high frequency path and a low frequency path. So the high frequency path is the top one. It consists of the input transconductors G21 and G22. So what they does is actually transconductors, what do they do? I mean, they convert the input voltage into a current, output current. And those currents are summed here at these nodes. And which amplify the input voltages, and the feedback transconductors G22 basically is amplifying the feedback voltage, V feedback, across these resistors. So at the output, you see the two resistors R1, R2. So they basically determine the gain. So the low frequency path is the lower one. Here you see the chopper. These chopping switches, you see these swapping switches, set of 4 switches which are swapped. So they basically represent chop. FC is the chopping frequency. On the right side, top right corner, you will see the timing diagram where FC bar, they represent the opening and closing. I mean, with this timing, these switches operate. So the low frequency pass basically essentially consists of a chopped and auto zero transconductor G51. So what is happening is we are also chopping and we are also auto zeroing this G51, which also amplifies V in, and a chopped auto zero replica transconductor G52, which also amplifies V feedback voltage. So the difference in their output currents drive the integrated built around this G4. This is in the middle, which in turns drive a transconductor G3. And this G3 output in the form of current goes through, it feeds the output stage that you saw in the form of G1. This is the output stage, G1. So essentially, this is a 3-stage amplifier. and it has like two branches, like two networks. One is a high frequency path. High frequency path have less amplifiers. Like here, we have less number of, for ease of understanding, high frequency path is what? Like we have less number of nodes and less number of poles. So less number of poles mean it has a unity gain frequency is much a higher frequency, but the gain is low. The bottom path is a low frequency path. Here we have more number of transconductors, so they are cascaded together, so the gain is high. The thing is, the chopping and the auto zeroing is employed with the lower frequency path. So these kind of amplifiers are called chopper stabilized amplifier, meaning by using choppers, one of the path is made accurate, more accurate, and the upper path, it doesn't have any auto zeroing, it doesn't have any chopping. The high frequency part doesn't have any offset cancellation. But by combining the two paths, we get the best of both worlds. Like our output will be offset free, will be flicker noise corner free, flicker noise free, and it will be like simple like amplification of the input without any non-idealities of the. So you can study, the paper, that's why I've just named it with the name of the paper, so they can easily study it if you are more interested. I just wanted to give you an idea of how all these instrumentation amplifiers work in principle. Like these are one of the latest topologies. Most of the work is done by Makinwa and the Huising group and TU Delft. So here, yeah.
Could you please repeat the portion where the portion of the high functionality path? Could you please point
Okay,
it out?
good. The high frequency path is the upper path, which is made by G21, G22 input and feedback transconductors. Basically, essentially, this is a current feedback instrumentation amplifier. Like this is the implementation of this topology. This topology. You see the slide?
Still
CFI.
at the next slide. So
I'm
take
sorry,
some
sir.
time to go back to the previous one.
Previous one.
So this.
Actually, it's still the next slide, that is one page chopper CFI. Now we are at the previous slide, yes.
Okay. So this is essentially a current feedback instrumentation amplifier. So what does a current feedback does? So it has a two set of transconductors like G21 and G22. G21 sees the input. You see V in input voltage, like the sensor's output directly connected to the G21. Okay. It has its offset. It has its offset V21. All right. Then there is a feedback transconductor G22, which has certain offset, of course, V22. Right. This feedback transconductor is basically connected. If you see now at the output of this amplifier, we have resistors R1 and R2. Okay. So this feedback is actually connected to, it's not shown by line now, but basically it's connected V plus minus V feedback is exactly the same voltage which you see at the output of R2 resistor, like plus minus VFB again at the R2, right? So basically this, yeah. So if we don't have anything at the lower, just forget about lower thing. So what we essentially have is a current feedback instrumentation amplifier, but the problem is that we don't have a chopper, or we don't have any, like we have these added offsets, V21, V22. So their offset is not cancelled, but they will perfectly determine the CFIA gain with the ratio of these resistors R1 and R2. Okay, so this is perfectly fine. Why do we employ, the lower complex stuff? Is basically we wanted to reduce the offset and the noise. So in order to reduce the offset and noise, what we do is we use the same transconductor G21 and G22. They're identical copies in the form of G51 and G52, the lower one. See, You see the lower G51 and G52? They
Yes,
are the
sir.
identical copies. Yeah, exactly. They will be the copies of G21 and G22. And now the lower ones, they will be auto-zeroed to reduce their offset, and they will be also chopped to again remove their offset and the flicker corner. And the combination of these auto-zeroing and chopping will have us lower flicker corner, will have us lower noise floor, will have, of course, we will have a chopping ripple, which will be taken care of by using a low-pass filter or by one of these integrator, or we there is another set of loop. Another loop can be added to cancel the ripple. That's called ripple reduction loop. So there's a loops and loops, but don't worry. I mean, they are all work. The basics are the same. They work in sync. If you design well, it's very easy. Like you can, I mean, join them together, and you will see. You will be amazed at how they are working in tandem with each other. So the overall idea, the finer details will be in the paper. The overall idea is actually like we are using a low frequency path, and we are making it more accurate using choppers and auto-zeroing. And by the help of this low frequency path, we are trying to get rid of the errors in the high frequency path. So this is the whole story. That's called, such kind of amplifiers are called chopper stabilized amplifier. Like using another set of identical elements, we are removing the offsets from the upper like high frequency path, which looks like doesn't have any offset reduction itself. But with since they are identical together, and then we will see how much offset is removed. This is removed by the ratio of the gain in the two loops. Like one will have, of course, one looks like a simple 2-stage amplifier, but the bottom ones looks like a 3-stage or 4-stage amplifiers. So the 4-stage one will have a gain, typically, they will have gain of around 200 or 250 dB, and the upper one will have a gain of 100 dB. So if the lower one has 200 dB, the upper one has 100 dB. So the difference in the two gains like 100 dB. So the offset and the flicker noise is removed by this 100 dB. This is the magnitude of. So this is a roughly speaking, this is how much stabilization in noise and the offset is achieved by the difference in the gain of the two paths.
Okay, sir, I got it. Jazakallah.
Oh, welcome. So this, I think, yeah, this might be too heavy for you. So I'll just go through. I think I'll just forget about a few other. I'll just present one of my topology, and I'll explain you also I'll show you the transistor level implementation as well. Like how is it done actually? So this is an example from my design. Can you see the slides now? Example from our design.
Yes, that's visible.
Okay. So see. So we actually did a flow sensor, and it's a very specialized process. You can see in the lower half, it looks like there are openings like MEMS die. You see a light greenish color. So this is a MEMS die, and you see a bluish color. This is a CMOS die. So they are like two wafers are wafer level bonded together, and in the greenish you will see two holes, big inlet and outlet. So this is for the flow of gases. So we wanted to measure the flow of nitrogen gas or any other kind of gas could be measured. So the flow has to be measured, and then the sensor that is used to measure the flow is very simple. It's actually a Wheatstone bridge. At the upper left corner, you see there is a op-amp feedback. We call it a heater control circuit. Most of the MEMS sensors, they needs a heater. So why do we need heater? We need to actually, with using heater and an op-amp in the feedback, we actually tries to maintain a constant temperature difference between this upstream and downstream resistors, RU and RD, which are arranged in the Wheatstone bridge. You see the Wheatstone bridge in the middle. So the Wheatstone bridge has upstream and downstream resistors. These resistors are actually shown in figure A at the lower left corner. So these are RU and RD. So the gas flows through these resistors. Like upstream will be the one from where the gas inlet, and RD downstream is the one from where the gas outlets. And in between the two is a heater element, RH. And this heater element is, of course, any gas which flows, it takes away the thermal content, right? So if a gas flows, you observe a bit cooling. Like if air is flowing, you will feel cooling. So what is cooling? Because the air takes away some heat away from you, right? Conduction or convection principles. So the same actually works here. So the flow of nitrogen gas takes away a heat, and the feedback ensures that the changes, it ensures a constant temperature difference, like 50 Kelvin is used. So this is actually MEMS design principle, like why do we need this temperature and how do we control that? But the circuit element is actually, we need to observe the changes. Higher the flow, higher the changes in the bridge output. And that changes are in millivolts or microvolts actually. In our case, they were like, I think, maximum 5 microvolt. And yeah. So we employ a current feedback instrumentation amplifier followed by an ADC. And together, interfacing CFIA and ADC, this makes our front end. We call it ROIC, readout integrated circuit. So this is the layout of this chip. You see the layout. It's very unique layout because it has like 2 wafers. One is CMOS and one is the specialized MEMS wafer. And for the MEMS wafer, we have openings. These we have 2 openings, and we have 2 set of these sensors. And between the openings, we have these, reddish color. These are the heater elements. And if you see, there's a very small layout. CMOS layout is a very small scale, almost on the right side. The size of this die is actually 4.5 millimeter by 2.5 millimeter. This is at the last I show you the fabricated die. It has these holes. These holes have to be, a very fine diameter tubes needs to be inserted for the inflow and outflow of the gases, so that we measure that. So these holes are for that purpose. The diameter of the hole was 500 micrometer only, 0.5 millimeter is the diameter. So here in the down right side, you will see the PCB where we have, we have the whole, like the testing. During the testing, we are inletting and outletting the gases. Then we are observing the electrical characteristics. So the next slide is how do we do the design? This is what we do is actually we do nested chopping. So you see we have primarily a current feedback instrumentation amplifier, CFIA. So we have 2 set of transconductors, GM in and GM feedback, followed by a 2-stage amplifier, second and third stage, which are together because, when we have 3 stage, we have nested Miller compensation. We have to compensate the frequency behavior, right? So we use nested Miller compensators, CM1 and CM2 capacitors. Their output RA and RB determines the gain because this GM in and GM feedback are designed identical. How are they designed? It is shown in the lower left corner. So we have a folded cascode topology where we have this M1A and M2A. These are the input pair. We have M1B and M2B. This is the feedback pair. So, and both of these transistors at their input, we are connected to 2 choppers. 1 chopper at the high frequency, 1 chopper at the lower frequency. Why I'm using 2 choppers? Because if I use 1 set of chopper, there are non-idealities as I talked about. We have chopping ripple and we have residue offset. This offset could be like easily this residue offset is 1 or 2 microvolt. As I tell you, my signal was 5 microvolt maximum. I have to bring down the residue offset to nanovolts. So that's why I use another set of chopper. By using the second set of chopper, I reduce this residue offset to 200 nanovolt. So this is one of the, very few designs published which have like nanovolt offsets. So in this design, we observed our nanovolt offset. Like by using 2 set of choppers, the input and the output of the feedback and input transconductors, we achieve this. And the how the second and the third stage are designed, this is shown you in the top right corner. So this is again a two-stage. You see, this is a two-stage amplifier. They are compensated with the cascode Miller compensation, CM1 and CM1B. So this is how, and this and the lower corner right shows you the measured noise performance. So the noise, input noise power spectral density that was measured 15 nanovolt per square root hertz. So the closed loop gain of this amplifier was 200. So this can be, I mean, we did it programmable like a set of RA, RB. You can change this RA, RB to vary your gain. And the flicker corner is pushed down to less than a hertz. You know, my flicker corner is pushed down to 400 millihertz. So to conclude this talk, we go through fundamentals of precision or instrumentation amplifiers. We discuss discrete components. Like, see, for your breadboard design, for your PCB design, you can do 3 op-amp amplifier by simply using, you know, when you are choosing your amplifiers, they are inherently like the off-the-shelf amplifier. They could have like chopper stability in them, or they could have CDS operation within them. Like these amplifiers are already like offset reduced. What you need to do is you just need to set the resistors around them to determine your gain. And if you have a luxury of a IC, then you have all the options open. Like you can have, you know, chopper amplifiers or switch capacitor amplifier or capacitively coupled amplifier or current feedback amplifier, any of this based on your choice or specifications. And then some examples from the literature have been presented. That's all. Anyone having any question, I can take it.
Thank you very much, Dr. Moss. From the audience, any question? Okay, let me start the question from Dr. Moss. Dr. Moss, right now we are in the thesis phase of the second batch of the MS, and I would like you to suggest some topic about the thesis, and I would like this kind of discussion to start from the students, and let's suppose some of the students interested in this kind of thesis. Is there anyone from the class? And Dr. Moss is the one person who contributed a lot during the last batch IC design project, so we would like to continue the same this time. Dr. Moss, can you spare some time this year?
Yeah, certainly. Anyone, you know, and all the applications that you have, like laptops, I mean, all kind of like sensors, they have these kind of instrumentation amplifiers because they are the foremost. I mean, the world is analog. We all know, you would have heard this, you know, so many times. So all these analog signals are very weak signals. You need to amplify those signals. So your first friend, which interface with those kind of sensors, you know, which gets this weak signal out for digitization by the ADC, is this block, instrumentation amplifiers. So you find it ECG amplifiers, you find EMG, you know, all these biomedical. So this is, I mean, really at the one of the most fundamental, and it looks like challenging, but it's not. I mean, if you can design the folded cascode, regular folded cascode types, then you just need to do few more operations. Like you need to do these, you know, with the set of switches, you need to do like either auto zeroing, or you need to with a set of swapping switches, like you do need to do chopping. And then you will be amazed to see like how powerful these two methods are. Simple but powerful. Like they will be reducing your noise and offset to like microvolts level, which previously were like in tens of millivolt. Yeah.
Thank you, Dr. Moss, very much, because that is very interesting topic, and I think I would look into some thesis related to this topic, and then I would also collaborate with you. And that's open for all of the students to think about this topic. Any other question from the audience?
So have you conducted such a thesis, which included such topics, the topic that you just explained?
Actually, I have conducted some thesis regarding the op-amp design, but the instrumentation amplifier, I didn't did any of the thesis. But I can think that I have just gone to this a little bit about this detail, and I hope with the help of Dr. Moaz, we can pull out some of good thesis in this topic.
Yeah, certainly. Hassan, this is just few more things with the amplifier design. I mean,
Yes.
it's regular amplifier design, just few more operations,
Yes.
right? So yeah, we should yeah, exactly. And this is the kind of work the industry is looking for. I mean, because anyone who is doing instrument amplifier, of course, he can do amplifier. Is the first thing is basically stability of 2-stage, 3-stage, and then few more operations.
And actually, we have some past history because the Sigma Delta ADC which we designed, and that was not my area before starting that project. And that also I collaborated with Dr. Moaz, and eventually we pulled out some very good project out of that. So I'm quite hopeful that in this one also we can have some good project.
All right. Thank you.
Thank you very much, Dr. Moaz. Any other question from the audience? सर मुझे लगता है इस टाइम पे सबको रोजा बहुत लग रहा है, इसलिए इस बार कोई क्वेश्चन नहीं आ रहा.
Yeah, happy Iftari.
So thank you very much for your time and for
Yeah.
such insightful talk. So actually, I have got huge interest in this topic, and I would definitely have some thesis in this one. And inshallah, I
Sure.
would bother you many times during that thesis process.
No worries. I mean,